We experience reality as a rigid container. Objects move through 3 dimensions of space, while a universal clock steadily ticks forward, driving everything from a falling drop of water to the orbit of a planet. For a century, physics has divided this reality into 2 distinct rulebooks. Albert Einstein gave us general relativity, which predicts how massive celestial objects warp the fabric of space and time. Meanwhile, quantum mechanics governs the chaotic, microscopic behavior of subatomic particles. This image is the cosmic microwave background. It represents the early universe, where immense gravity and quantum scales existed in the same place. When physicists try to force relativity and quantum mechanics together to understand these conditions, the equations shatter. The two frameworks contradict each other. In the late 1960s, physicists John Wheeler and Bryce DeWitt tried to fix this by writing a single quantum equation for the entire universe. But when they finished the math, they found a glaring anomaly. The variable representing time canceled out of the equation. The math points to a universe that is a static, frozen state. At the most foundational level, there are no spatial dynamics and no passing time. The past, present, and future are locked in a single moment. If the math governing the base layer of reality lacks a ticking clock and moving dimensions, then our 3D experience is likely an emergent property. Space and time appear to rise from an underlying source code, quantum information. To figure out how the universe processes that raw information, theoretical physicists test their math against the most extreme objects in nature, black holes. Stephen Hawking and Jacob Bekenstein discovered a strict limit to how a black hole handles data. They proved that the maximum amount of information a black hole can store is dictated entirely by the 2-dimensional surface area of its event horizon, rather than its internal 3-dimensional volume. Juan Maldacena scaled this concept to the cosmos. The ADS-CFT correspondence applies the black hole limit to the universe, suggesting reality is holographic. He showed a 3-dimensional universe with gravity translates perfectly into a flat 2-dimensional quantum field on its boundary. The math holds up on both sides. Space functions as a holographic projection emanating from lower-dimensional quantum data. That gives us a mechanism for space, but the frozen clock problem remains. In a static hologram, how do we experience a passing second? Paige Wooders describes time emerging from entanglement. Imagine a universe with a clock and observer. To an external observer, the global state is completely static. But inside, as the observer entangles with the clock, their relationship creates change. The clock appears to tick. Time is the localized internal experience of quantum entanglement spreading through a system. The math for holography and emergent time is consistent, but physics requires physical evidence. Does a holographic universe leave traces we can actually detect? Researchers at Fermilab designed an instrument called the holometer to answer that question. They hypothesized that if continuous space emerges from lower-dimensional quantum data, there might be a physical pixelation, a high-frequency jitter in the fabric of space. They ran the experiment, probing space down to the Planck scale. They found no evidence of this local quantum jitter. This finding narrowed the search. It established that if the universe is a hologram, the encoding is highly non-local, behaving like a robust quantum error correcting code, rather than a collection of independent, localized pixels. This leads us to a fundamentally different view of our world. Space, time, and gravity are simply macroscopic illusions. Think about the physical feeling of heat. A single atom doesn't have a temperature. Heat only emerges as a thermodynamic result of millions of atoms colliding. Space and time operate the same way. They are descriptions that emerge when millions of quantum states interact. This framework solves the black hole information paradox. It indicates that the data of anything falling into a black hole is preserved on the 2-dimensional boundary and returned to the universe via encoded correlations in radiation. The universe is a vast, interconnected web of quantum information. The 3-dimensional reality we experience is the physical manifestation of its entanglement.